coming from Delft. The last 25 years of my career in Delft. But when I was looking for this lecture room, actually I had to look a bit because I didn't know the address. So when I when I went to enter, I said, hey, this is the exact location where I held my master's project presentation, which is about 30 years ago. Here in this room with this. So I originated from Eindhoven, this is my program. But afterwards I went to Delft and I'd like to give you a bit of a flavor of what it means to let's say, become part of the control systems group, what we do in the control systems group in terms of research and education. Opportunities are there for master's group. Well, I always tended to say, given the size of the audience, I'd like to make a really interactive kind of session. So if you feel like getting into the discussion, please do. If you have any questions, just you can stand still at certain points in the presentation. I think it's more explain. I probably have way too many slides anyway, so I'll just glance through them and just stop at the points where I think it might be effective to say a few more things about it. Control systems. Well, you probably have a picture about what control systems are, and most of the engineers, especially EE engineers, students have had several courses in control, in dynamics, in feedback, in closing loops, in tuning controllers, doing all kind of works on dynamical systems. So that's probably the easy part. I'd like to start with a statement actually that says, well, model-based control and optimization is the leading paradigm in the optimal operation of dynamical systems, and that's a very wide one. So if you look around in the, let's say, technical environment of society, in the engineering environment, you see very many what we call systems. Now, of course, the word system is a bit misused by many people. Or you could say, well, every particular field of expertise has got its own notion of a system, whether it be electronic systems or communication systems. So when we talk about systems, we talk about dynamic systems and basically all the technology out there that is governed by some kind of differential equation. Or if I usually explain to mechanical engineers, you just kick an object, it starts vibrating. That's the differential equation that you basically see. Now, of course, that happens in mechanical engineering, but it also happens in electronic circuits, it also happens in electricity networks, it happens in cars, in batteries, energy management there. It, of course, happens in the old famous ASML type of systems, where we have to position objects very accurately. It happens in the process industry out there, the chemical process industry. This is the electron microscope. This is in the oil fields exploration and production. This is in laser interferometry. Inkjet printers also. And that's sometimes also a bit of the problem of control, because if you have to explain to your grandmother what you're doing if you are in control, it's a while. We are controlling, at the time when I was studying, we were controlling control systems in CD players. So you're working on CD players, not only CD players, but we're also working on energy management systems, and we're working on process control. But these are domains which really don't seem to interconnect with each other. But if you look at all the problems underlying these areas from a dynamics and control perspective, they do interact, and they're very much in common. And at least for me, that was one of the challenges of that field. And I think it's also still one of the challenges and attractive features of the field, that you're studying something we call systems and control, but you don't really limit yourself to one particular field of application. And it also is clearly visible in the directions that people take when they graduate with us, because they arrive in different types of industrial sectors. Now, just to make a few general statements about control before we go into the research things and all the subjects that we treat, but just from a user's perspective, from your perspective, how do control people look like? How can you characterize them, not only during the study, but also later on in their careers? Control people, you can have a very generic set of tools for describing dynamical systems, or describing dynamics. Of course, you recognize the simple feedback loops, but the thinking in terms of cause-effect relationships, in terms of feedback loops, in terms of optimal responses, in terms of disturbance rejection, Thinking in terms of stability, of course, also a very important one. And a generic set of tools is something that you take with you as a control engineer, which appears to be very important also later on, because it gives you a very structured way, for thinking about technological problems, not being restricted to the mechanical engineering implementation or thinking on the physics or the electrical parts or the communications parts, but seeing all the things just as part of one big picture and being able to connect them. So consider interrelations between technological systems across several domains because of their systems thinking. Systems thinking has become quite a well-known, let's say, qualification. Thinking in terms of cause-effect relationships, in terms of interactions, in terms of ordering of operations, and in terms of feedback mechanisms. May sound a bit abstract, but I think it's really very important. As a result of that attitude, control people therefore play often a very central role in innovative technology development. On one side, on the other side, their role might not be so very much apparent. If you hear people talking from ASML about their wafer scanner and what they can do, usually it will not be the control people telling you about what's happening. Although they play a really central role in getting all the sides together. Because of course, you can imagine that without any serious feedback, there would be no way of accurately positioning a mechanical object within, let's say, 5 nanometers of accuracy. You just are not able to do that. So control is very much central, but sometimes also very much invisible. Your car these days has very many control loops, but you hardly notice that. It just serves to the people who are using it. Okay, continue along this road. Are strong in multidisciplinary teams, so because of this generic set of tools, control people typically are very well able to cross these boundaries of traditional disciplines. And if you're working in a process technology environment, industrial process environment, you have to talk to the chemical engineers. If you're working in an ASML type of project, you have to talk to the physics people, or to the mechanical engineers, and to basically map their input and their thoughts to their own field. And that's something that people trained in, and I think that's a very strong asset also. Have strong analytical skills. We do mathematics to quite some extent, but also, of course, we're also using it for a particular technological purpose. But the basic theory that we have available is mathematics as our language, systems theory that we particularly use, and that we develop also in order to create new methods and new tools for solving new problems. And as I said, we are not tied to one field of application, so it doesn't predetermine you for working at a particular job, at a particular company. And of course, that's like many other engineers are never jobless. Never had a control engineer having no job. Sufficiently number of jobs out there, interesting jobs out there on the market. Okay, so this is a bit of the perspective, maybe from your perspective, hey, what could that offer you? Now, what are the ingredients? I mean, the principal scheme you recognize very well. That's, of course, the very simple control schemes that are there to tune simple servo loops. But you can imagine, starting from the things you've seen in your bachelor courses, the field has been developed to much more higher degrees of complexity. In all kind of distributed ways. These days we're thinking about dynamical systems as distributed systems with very many different connections, where you have decentralized actions, where you have some centralized objective to attain. We can think of schemes like this, or in biological systems, dynamic networks like this, where you use these kind of tools for classifying, characterizing the chemical reactions that take place in the cells. All this stuff of kind of keywords like we do modeling, because model-based approach is very common. We think about methods for model complexity reduction. We do system identification, so we identify models from data, particularly elective course also in the master's program, how to construct physical models out of measurement data, rather than from the first principles relations that you have available. We do model-based control, optimization, estimation, detection, design, sensing, actuation, adaptation, learning, autonomy, robustness analysis, and of course also control as part of systems design. And one of the developments that you see is that control actually started as a kind of independent field within electrical engineering in the time when electronic circuits had to be designed and understood, like in the 50s and 60s, for instance. But the area shifted to quite some extent to the mechanical engineering domain, where the robotics was there, and the mechatronics popped up, and mechanical objects had to be optimally controlled. We moved from electronics to mechatronics, and to some extent we're also moving to chemotronics, where we would like to control chemical reactions. But it takes another step, because the chemical engineers typically don't have that much appreciation for dynamics. They are more, let's say, eager to think about processes as operating something which is operating in steady state. So don't touch it. If it works, don't touch it. Don't change it. But of course, all of our world, all of our technological world is getting more and more dynamic. It's going to change. You have to adapt to changes in the environment. You have to move fast. You don't have time to wait for the steady state. You really would like to optimize control efforts in it. So one of our challenges is to convince the chemical engineers that we might benefit from each other more strongly. But that's also to some extent the way to go. Okay, what do we do within CS? So we have this, what I call this yellow area of the fundamentals of signal systems and control. There we study the basic principal methods of signal analysis, of control theory, in all kinds of forms and shapes, about modeling in all kinds of forms and shapes. But control, we can only show what we can do by moving into application domains and apply control there and develop control algorithms for these particular domains. So that's why the interaction from, let's say, our fundamental area to the environment, as we call it, to the application domains is very much important. And typically for a control group is that we are not the owners of these application domains. We work on energy systems, but of course the energy systems are really owned by the people from the EES department here. And we work on automotive systems that may be less specific. We work in high-tech systems together with the people from EPE and the power electronics. We work with industrial chemical processes with the people from chemical engineering. And so, in order to show this benefit of control, we really have to, let's say, cooperate with this outside world. Otherwise, we just are a mathematics group doing control methods. And we're not that. We do really connect with this outside world. Now, these domains, of course, well, they're quite different, especially if you look at the spatial scales. In the high-tech systems domain, working on the ASML type of problems, we deal with accuracy to nanometers, position mechanical objects for the next few 5 nanometers. In industrial processes, we work with Shell on what we call reservoir engineering. I'll give an example of that later on. So that's in the exploration and production of oil from oil reservoirs, and you're talking about reservoirs of kilometers in size. So in terms of the comparison with the nanometers, that's quite different. And the fun part, I also like to say, is that the people working in this domain and the people working in this domain still share offices and can talk to each other about their techniques. Because the application might be different, but the underlying problem of how do you control dynamical systems governed by differential equations, the basics there are still the same. Which I think is very good. Okay. Of course, in all these domains, then we have, let's say, intensive relationships with industrial partners. The straightforward ones in the high-tech systems domain, ASML, PHY, NXP, you can imagine. ProDrive, also a very important one, power electronics, mainly for ASML. In the energy domain, I will give an example of that also later on. We're working on with the energy companies, and there the principal challenge is actually that the whole electricity grid, as you probably know about, the whole electricity grid that used to be a very stable, steady-state, operated system, these days with all the decentralized power conversion and power production and the decentralized use of energy, is going to be just a huge dynamical system where very many players connect to supply energy withdrawn from the network again, and then the whole system needs to be balanced. And the control of that is a serious challenge for the future. Especially also with all developments in automotive systems, where you can plug in your car to charge the batteries at any moment. It may be quite a challenge to have an electricity infrastructure that does a good job there. Okay, process control. The nice companies ABB, Sasol in South Africa. DSM, Shell is a very important one. We're moving into food now also, a new project with Friesland Campina. And then the automotive sector. We work together with Dafne for this is the people that we're working on. So one colleague, food professor, Professor Steve Weiland, you probably have seen one of the bachelor courses, yeah? Optimization. You haven't seen me yet in the bachelor's program. I will start my first course on systems next quarter, the first year. So, and now involved in master's education already. Paul van Vos you have seen in courses. He is about to retire, so that's why his picture is a bit smaller than the rest. So he probably will not take any new students along, but he's still involved in that group to some extent. The younger people, Michel Lazare, Roland Todt, Ben Oskan, and actually since this morning, maybe next week I could have the picture there with a new assistant professor on automotive systems, because that's an area we are going to further invest in. Young, enthusiastic people with a very strong position in research, but also with a strong drive to provide excellent teaching. That's also been the atmosphere of the group. I think from the past also that many of the people from the group, like Paul van Vos and Steve Weiland, got several awards for their teaching performance. So it also indicates that our group is quite eager to provide excellent teaching. I think that's important. So not just a research group who considers teaching to be, just part of the job that has to be done, but we think that raising students is an important thing, because we like to attract good students to our group, both as master students but also as PhD students and researchers. International, we both are Dutch, Romanian, Hungarian, Turkish, and Dutch again. So we'll have a mix for the international environment. And in order to take care that we can effectively communicate with this outside world, we have several part-time professors in the group, but related to particular, let's say, application domains. Tom Bax, you know probably as dean also of our department. He's in process control. We have two part-time professors from ASML, Hans Butler, from the mechatronics domain, 1 day a week, and Wim Koenen, with a more stronger physics background, process control in lithography. Henk-Jan Bergveld from NXP, especially working on energy management and battery management systems. And John Kessels, part-time lecturer, involved in automotive systems. You probably also have seen John, I think, in the bachelor programs. Probably only if you've taken some automotive minor. So with these people, they typically work in a group 1 day a week. And are very helpful also in our projects together with industry, supervising also students and professors. We have got 20 to 25 PhD students, on average, 15 to 20 master students a year, and the master students come from 3 different programs. So the electrical engineering program, that's the first one. We have the systems and control program that we are involved in, and the next presentation will be an systems and control program, so we'll not say too much about that. And also students in automotive program. We haven't had so many of them. Okay, I'll just give a few examples of the projects and activities that we're doing in the several domains. Time is not running fast, so let's see what's happening. So if you look at high-tech systems domain, which is of course a very important domain for this part of the country, the Eindhoven area with with ASML and Philips and all the high-tech companies that are, I would say, very famous and also very active in the development domain. And of course, let's say in the most principal problems there, of course, there are very many problems related to the ASML machines and getting them into the next generation of improved accuracy, have reduced line width of the connections and reduced overlay of the several patterns. I assume that I can talk about ASML machines as is, and you have seen these things before, I guess. Yeah, several times probably. And of course, you can picture there that the whole operation of these machines is a very tricky issue, a very challenging issue, because how to position, mechanical objects on top of each other with an accuracy of less than 5 nanometers, with completely independent movements. Without control, that would be completely unthinkable. And so it's amazing there to see also what you can do with actually just a simple mechanism of feedback, because feedback is the only thing that can create this. Measurements, measure where you are, where you should be, have a very fast measurement and actuation loop which drives you to the right position, and of course that requires a very accurate modeling of all the phenomena that take place in this setup. And you can imagine if you start moving an actuator, position the mechanical stage from location 1 to location 2, only the movement itself creates all kinds of vibrations in the machines, which have to be dampened out again very accurately. So control plays an important role. Not only working on the lithography with ASML, also on electron microscopes, with also basically positioning problems. And even also with OSE, if you think about inkjet printers, they're the exact control of droplets of ink of the right size at the right time is also one of the high-tech problems that we're looking at, where you can imagine that if you have ink channels that are situated closely together, that the actions that you take in one particular reservoir part have effect on the other reservoirs, on the flow behavior there. You have to take account of that in order to have optimized printing performance. So what do we do in this high-tech domain? You see the bit of the longer trends is that in, let's say, in motion control, in mechanical movement and the control of that, of course that's a topic which very strongly belongs to the mechanical engineering environment, how to control mechanics. One of the things that you see, is one of the examples of the wafer stage from ASML, on stage 2-level type of actuator. One of the developments that you see is that actually in these actuation mechanisms, in these ways of controlling motion, you see kind of trends where it seems that the part of mechanical engineering that is involved, the part of mechanics that is involved, is somehow reducing, and we get more and more of the electronics and the electromagnetics elements in there. We move away from the more strictly mechanical actuators to schemes that look like this, in a very abstract way, where you have a coil plate and the mass on top of it with permanent magnets that you would like to just move as a flying carpet without any wire connections to the object that is moving. Because you can now imagine that in these days, wafer scanner mechanisms, the fact that the moving object has got wires connected to it is a serious source of disturbance. Just the fact that there's a wire connected. And of course, with electromagnetic forces, you're able to control the position of a floating carpet in a very accurate way. However, the technology that's required for that is quite, from a mathematics point of view, it's not so easy. There are all kind of nonlinear relationships that you need to take care of all kind of spatial mechanisms that you have to take care of that are really quite challenging. It's over here. So you can imagine the kind of classical way of creating accurate position control now is to have a long stroke motor with air bearings and a short stroke motor that takes care of the very accurate positioning, again with wires connected. The next stage, the current stage, is a long stroke motor with a magnetic bearing and a short stroke motor on top of it. And the future would be just to have a floating carpet that is positioned just the way as you would like to have it. But then of course you get mechanisms like, hey, the mass here you would like to have not as high as possible. You might have a lightweight construction, but then when it's lightweight, it also can create all kinds of flexibilities in its structure. So in order to create this, not only just a flying carpet, but having a flying carpet which is extremely stiff, which doesn't have the flexible modes, you have to actuate and to measure spatially distributed over space and take local actions in order to control the movement and the position. These are the typical projects that we do, you can imagine, in cooperation with EPD.
So here you're using magnetic fields to move the plate. Does that have any effect on the process that you're actually trying to do on top of the plate? For example, I mean, you're doing some chemical things, right, on top there. Does it affect it?
Of course, the intention is that it shouldn't affect it. Of course, these are, let's say, the boundary conditions, like the electromagnetic mechanisms, so should not interfere. You also have mechanisms like, okay, how is the rest of the surroundings? They do have to operate in vacuum. I mean, that also kind of limits the kind of technology that you can apply. But so far, we have been building a prototype setup of this that's available in the EPD lab, and that's just subject of research. This is typical of the type of project that both ASML is working on. We are working on here with support of ASML as one of the technologies that is, about to be there to get copied into the new generation machines. But that's still a bit of a debate, not only about can the technology do it, but also, the industrial people have sufficient trust in this new technology that it will be reliable for, the next generation of machines. So that's partly solving technical problems, but of course it's very, very much related to that in order to convince the ASML people that this would be a good technology. That also holds, by the way, in general, for the topic of multivariable control. We already discussed with ASML, I think 10 years ago, that at some point we should really look at, combining different control loops into one or to several multivariable loops, as we call them, to take account of interaction. So far, they've been training themselves so very well in tuning single loops that they could still develop this full machine with only what we call CISO control loops, single loops that don't take account of interaction. They still reach nanometer accuracy. So that's an example of a situation where we at the university might think, hey, come on, there's much more advanced technology available. But industry says, look, if we can do it without tools, then what's up? And they've got a good point there, I think. So the challenge is on us to show that we really need the tools that we're developing. I'm quite sure that they will hit the wall in a couple of years and they will move to the multivariable loops anyway. Okay. I was running fast. I have to skip a bit. One of the other things that we are now working on in the lithography application, that's also in the ASML machines. It's not the moving mechanism, but if you think about the light source and what's happening with all the light that's transmitted through the lenses, and that is being projected onto the wafer for projecting the circuitry there. Now, if you look at the power of the light, which is available, and the power that really is absorbed by the surface where it gets onto, I think only 2% of the power remains there, and the rest is just, it's just along the way gets absorbed into the mirrors and to the optical system. That's not so much of a problem. There's more power in there, but that power in the lenses is, of course, heating up the lenses, and heating up the mirrors, create deformations, and as a result of that, create a distortion on the pattern that's being projected. So far, that's never been a problem, but in current days, just identifying which part of the machines are the most critical parts, this thing is now popping up as one of the critical things. So as a result, we have to study that, build extensive models about how the lens systems are being affected by the heat of the light, which is quite detailed. You really have to go into physics there, build dynamical models, and try to incorporate this model again in the control loops that you implement in order to position your weight. So you're basically correcting for the aberrations that occur at the lens level. You correct at locations where you can interfere with that. Okay, power systems. Already said a few sentences about that. That's probably also the best summary. So in the power systems domain, we are moving from the really steady state grid with very few players in the field towards a really dynamic operational grid where very many players supply energy, use energy in a very dynamic market, and the problem is how to control it. And what kind of control normally do you have there? And of course, again, we did it together with the EES group. They are the experts in energy systems, but we're looking at it from a dynamical systems point of view and see, hey, what kind of tools could you provide to the particular players in the field in order to play their role, to optimize their interests, their profit, you could say, but still have a guarantee that the whole system remains stable. And that's still a huge challenge, because this dynamical system hardly has any boundaries. It's not just the Dutch system that we're looking at, but the Dutch system is connected to the Belgian one, the German one. And all these systems are connected. And locally, control actions are taking place, which affect actually the whole network. So this is far beyond the system that you say, okay, you have a very complex network, there's one control system on top of it that controls everything. No, that's not happening. You've got decentralized control here, or distributed control, you could say. And somehow we have to take care that the actions get coordinated. And pricing mechanisms are one of the actuation tools that you could implement. So making something more expensive or something cheap influences the behavior of the several operators and could be used as a tool to stabilize and increase performance. And then we get into the dynamic systems area again and into our field. Review the time, let's leave it with that. Automotive domain, well, you can imagine that there's quite some dynamics also running on in automotive. We're particularly focusing at the moment here on everything that's related to energy and battery management. And batteries are quite awkward things. The performance of batteries, the performance assessment, so how to detect how much power there's still left in my battery is not so very easy. And also optimal ways of charging and recharging, depending on whether you need them, is quite a huge phenomenon. Looking at hybrid trucks and projects around that, but called plug-in hybrid full electrical vehicles, where you can even think, and that's in relation with the previous subject. Now, of course, all the cars that are driving around and the batteries that are in there also serve as a kind of energy source, energy storage, actually, which to some extent could be related to the things that happen in the electricity grid. So mechanisms like you drive the electric car, arrive home, you plug it in, you like to charge it, but somehow the system decides to charge it only, let's say, during the night because the energy is not really available, or just in the next hour. You see that all kind of dynamical phenomena get into play. Okay, what I'd like to see is to say a few more words on is process control, because that's something completely different and also a bit newer to this, let's say, Eindhoven environment. It's a subject that I to some extent also took with me from Delft last year. You can think of all these huge industrial processes where there are many challenges of doing control and optimization and going into adaptive and autonomous control. But there's one area that's, I think, particularly challenging. That's the field of reservoir engineering, as we call it. We do it in cooperation with Shell and a couple of other oil companies. Very briefly stated, you picture an oil reservoir as a kind of pancake of oil which is situated somewhere in the subsurface, could be very deep. How do you produce oil? You find a location, drill a well, the pressure is down there is very high, so it starts flowing itself, and have a bucket, collect the oil, sell it on the market. Very simple technology, basically. But relatively soon in the life cycle of reservoir, the pressure goes down. Pressure is not high enough anymore to have this oil floating to the surface. And in earlier days, oil companies would then just move to the next location and drill a new well and redo their job. But there's still 65 or 70% of the oil left in the reservoir, so you could do some additional action to produce that oil. So the way that is being done is that typically additional wells are being drilled, and you bring water pressure down to the reservoir, so you just bring water into the wells, and then start pushing out the oil with water to the location where there's what we call a producer well. This is a typical example of a reservoir with a simulation environment where there are 4 producer wells, the red ones, and there are 8 injector wells, as we call it. So in the 8 injector wells, water is being inserted. The pattern what you see is the what we call the heterogeneity of the reservoir. This, of course, it's not a swimming pool of oil. The oil resides in the pores of porous rock, and this rock has a property that in some directions is much more easy to press than in other directions. In every location of the reservoir, you've got what's called permeability, and the permeability indicates how easily the oil flows. And typically, you have patterns like this with, let's say, former meandering rivers or sandbanks that are in that area down there. You can drill wells. The idea is they're vertically drilled, but you can drill wells in all kinds of forms and shapes. And when they are drilled, you can even afterwards decide where you have openings in the wells that you can control remotely. You can control the openings from the surface, and so have you can picture a multi-variable control problem where you just switch the valves of the injector wells, even switch the valves of the producer wells, in order to shape this oil water front, which is going to be pushed to the other side. So here's the here you see the example of this pushing, where of course blue is water and red is oil. And you see the oil being pushed from the blue valves to the red ones. And of course, if you push in a non-smart way, you just push the water from the injector wells to the producer well, you're just pumping around water, so you don't produce anymore. So the trick is there to do it in a very balanced way, to end up at a moment that all the oil has been produced. What you see here is the valve settings of the injector wells and the valve setting of the producer wells. And if I repeat it, you see that they are dynamically moving. Here's a static approach, they call reactive control. Here's an optimal control approach. We've optimized for the control setting. So here we have dynamically just operating the valves in a smart way in order to optimize the oil that is being produced. And you see that we gain 8% more oil of the reservoir, which in the cooperation with Shell is very attractive to be able to show, because it gives you enough research budget for the next project. By the way, this animation was being programmed by one of the master students who did the project on this. And the nice story about it is then when he showed it to me, I said, oh, but now you have to show it also to people at Shell and Rijswijk, because they will like it. It's a kind of picture about what you can do with more smart technology. And then when he presented it in Rijswijk, I think within 3 days it was on the desk of the CEO of Shell, Jeroen van der Veer at that time, as an example of, hey, this is what we can do with what's called smart well technology. So this is a very nice project in cooperation with Shell and with the people from civil engineering in Delft, and with several oil companies, Eni in Italy, Statoil in Norway, Petrobras in Brazil, because all the oil companies nowadays are working on new technology to control these wells, to optimize these wells' behavior, which is really interesting. Okay. Let's see. I think I would like to move to some more overall pictures. So our educational activities, you've seen people from our group in the bachelor program, several courses, system courses controlled. There's several courses in the master program too. Typical for 20 to 60 students that take our courses. We are involved in 3 master programs: electrical engineering, systems and control. We'll hear more about that in a few minutes. And automotive technology. Our master courses are very often done in cooperation with our colleagues from mechanical engineering, because there's also an extensive control group, and of course we team up very effectively with the groups. If you're interested in our domain, we have 2 mini programs that we suggest. I think they're on slide here. Yeah, these 2 ones, the 1.1 and the 2.1. So that's typically the first thing that you do if you're interested in this domain. You're going to follow these mini programs in the September, October, November kind of period. They're not the most easy ones, but yeah, that's life. That's also the challenge of the master program. Yeah, elective courses, graduation projects, that's all relatively standard, I think. We appreciate it if you come by and make an appointment with one of us, either with Steve Byland or with myself. If you think, hey, this might be an interesting area for me, just make an appointment, come along, we'll have a discussion. We'll try to advise you also on electives. We're going to start up a discussion where you could do a traineeship, either internally or in industry, or get an extensive international network for people who would like to go abroad. Several people spend their traineeships in China, that's now going on to Canada, New Zealand, Australia, and all kind of locations available. Elective courses selected from several programs: electrical engineering, mechanical engineering. We also have a national research school called DISC, Dutch Institute of Systems and Control, where we nationally cooperate and offer a PhD course program. And for the excellent MSc students, it's also open to take one of the courses there. Yeah, let's say the choice of elective, of course, you kind of discuss with your supervisor, but there's a large degree of freedom there. And we stimulate also not to take only courses in control, but to develop this a bit more. The master phase, I think, is a very attractive and challenging phase. I will always describe it typically the phase where you make this transition from sitting in classrooms, studying material that is offered to you by a lecturer, doing the exam, into a phase where you really become acting as a professional, where you develop your own problems, not only your own solution, also develop your own problems and work on it solution-wise. I see people getting more and more enthusiastic also in that phase, so it's also quite fun to see. There's a lot to be chosen. There are many things that you can choose. If you need help in making your choices, just seek the help. I mean, we are there to support you and to guide you. Go for high grades. This is the time to invest into your career, I think. I think that is really challenging. Exceed your own expectations, develop yourself. Just for the students also, we have just installed last year mechanism of an MSc workshop. For every last Friday of the month, we meet with all the MSc students, staff people, and all students there. A few students give an informal seminar about the status of the project. There's some discussion, they get help from colleague students, get help from us, get feedback from us. And we typically close that morning with a guest speaker, which is a former CS student who's now somewhere out there having a job, and he's telling about his career, what kind of choices he made, or what kind of work he's doing. Gives you a bit of a perspective about, hey, what is there after the MSc program, because I think that's also important. This is a selection of MSc students. You see, we've got a nice mix of males and females. It's better than the audience now, isn't it? Okay. Questions from you? This is my part.
So in the beginning you said that you work closely with other research groups in electrical engineering.
Yeah.
Is it normal for people who are doing their master, for example, at EPE, to be part of their master thesis working with you guys, or?
Yeah, we have several research projects, and these also PhD students, working in really close cooperation with PhD students from other groups. Typically with EPE, we've got more like this kind of teamwork where typically we work on a joint project, one PhD student from CS, one PhD student from EPE, and they kind of team up. And in that team, master projects are available. And then students can choose whether they, let's say they follow the EPE program or they follow the CS program, but typically if they follow the one, they will also take courses from the other. So there's a lot of flexibility in making up their choices there. That happens with EPE. That happens to some extent with EES also, maybe a bit less, but EPE there is the most natural one of the rest. But the same thing also could happen with mechanical engineering. Yeah. Any other questions? No?
Well, then, thank you for the presentation.